Hello and welcome to our next module. We're today going to start looking at functions that are no longer linear. So let me just remind you of what a linear function looked like. Remember when we were dealing with linear functions, that meant we were dealing with things that when you graphed them were straight lines. Well, today we're going to be looking at what are called exponential functions. So we're going to be graphing things that are not straight lines. So today in your notebook, you're going to need to start out on page 489. So pause the video if you need to. Go ahead and find page 489. And on that page, you should see a couple graphs that look like this. So a couple things I want you to do here. Let me get rid of some things here for a second. There. Let's start with a blank slate. What is the difference between linear and exponential? So you should see this graph on page 489, but I want to show you the difference between the two because these two graphs look the same. So it might help to have a highlighter here. On this first graph, I want you just to highlight everything that says linear, right? And highlight the linear graph here, the one that's a straight line. That's what a linear function would look like. On the one that says exponential above it, go ahead and highlight exponential, and then go ahead and graph the part that shows an exponential function, and that would be this curved line right here. That is my exponential function. Now, there's another way to tell the difference. Anytime you have a linear function, your output is always changing because you're adding or subtracting something every time. So if I am adding or subtracting, adding if it's going up, subtracting if it's going down, then my function is going to be linear. If I am multiplying by something, then my output is going to be exponential. So go ahead and turn to page 490, and we'll look at an example of that. So look at page 490 here. So let's start over here. When I look at the data here, we're going to fill some things in below here first. So go down to where it says underneath that data, magnitudes of 1 and 2. You've got some missing information in your notebook here. So anything that's highlighted on this slide, you need to fill in your note sheet. Notice as the order of magnitude goes from 1 to 2, that the TNT increases from 0.6 to 6 tons, or it's gone up by a factor of 10. Now find the section right below that that says magnitudes of 2 and 3. And notice that when the magnitude goes from 2 to 3 in the table, the amount of TNT goes from 6 tons to 60 tons, or again, increases by a factor of 10. And when we say a factor of 10, what does that mean? It means we're multiplying by 10. Remember, factors imply multiplication. So let's go back up and look at that table. When I went from 0.6 to 6, that increased by a factor of 10, or I multiplied by 10. When I go from 6 to 60, I multiplied by 10. When I went from 60 to 600, I multiplied by 10. Notice every time we take a jump in the output, it happens because we've multiplied the previous output by 10. That would indicate an exponential function. That's how we know it is exponential. So let's skip over to page 491. Let's go and look at that page. And here they give you kind of a definition of what exponential is. Again, let's start with a clean slate here. So we're looking at page 491, and they give you a definition of exponential here. Now, here's a function that's exponential. F of x is equal to a times b to the power of x, or it doesn't have to be f of x, it could say y, so it could look like this one also. Now, that function is going to be what we call a growth function when that term b is greater than 1. So that's something you may want to highlight on this one too. It's exponential growth when b is greater than 1. Now you can also have an exponential function where b is going to be between 0 and 1. What that means is it's going to be a fraction or a decimal. Then we call it an exponential decay function. So I would maybe write this next to those definitions. What does an exponential growth function look like? It's going to look like this. what does an exponential decay function look like? It's going to look like this. One of them is increasing, one of them is decreasing. And these graphs are going to have what's called an asymptote. That's a word we haven't used yet, but the definition of that is a line that my graph is not going to cross. So as this graph gets bigger and bigger, it's never going to cross this imaginary line that lands right here. As it gets smaller and smaller, it's never going to cross this imaginary line right there. That's what we call the asymptote of that function. Now, let's talk about what these terms mean here. So you might want to write this at the bottom of the page. You'll notice you have two graphs down there. One of them looks like the growth function. One of them looks like the decay function. You might even label them there. But you can see that's divided up into growth on one side, decay on the other. But when we have this function, f of x is equal to a times b to the power of x. What does a represent? A is always going to be the initial amount. What are you starting with? B is going to be the factor that we are multiplying by. So remember that it's growth if that factor is greater than 1, and it's decay if that factor is between 0 and 1. And x is always going to be a reference to time. Now, it may not be days, it may not be weeks, but it may be the number of times you do something. It might be what the x is representing. So go ahead and take your note sheet, and let's turn to page 492. Let's look at this problem. Here is an exponential function. We're going to take a piece of paper and we're going to fold it. And every time we fold a piece of paper in half, it's actually going to get twice as thick. So this is a function that will tell us, okay, how thick is this paper going to be if we fold it X number of times, right? So a paper with X folds. So that's going to be my time, right? It's how many times do I fold this paper? Now, notice there are some things here. What is the original amount? The original amount was A, this number here. Well, how thick is our paper to start with? Well, they tell me right there. It's 0.5. What happens to a piece of paper when I fold it? Well, it doubles in width, right? So why are we multiplying by 2? Because the paper is going to be twice as thick. And then X, that's how many times I'm going to fold it. That's going to be my exponent. So if I wanted to evaluate this function, all I need to do is put numbers in for X. So at the halfway point of this page, go about halfway down, page 292, you should see this table. And notice I've got some numbers filled in for you. Now, where did these numbers come from? Well, they just took this expression. Notice they've already filled in X for me. They took this expression and they just typed it in the calculator. Typed it in the calculator just the way it looks. 0.05, in parentheses put a 2, and then you know how to put exponents in the calculator now. Remember, you need to use the caret key, and then anything behind that will be your exponent, so follow the caret key with -2. If you put that function in the calculator, you should get 0.0125. Put this function in the calculator. You should get 0.025. Go ahead and try it with 0. Now this one I don't need a calculator for because anything to the 0 power is 1. So 2 to the power of 0 is 1. 0.05 times 1 would just be 0.05. Go ahead and pause the video for just a minute. See if you can fill in the other 4 values in that table. All right, hopefully you took a minute. You tried to find those on your own. If you did, here are the values you should have ended up with to finish out this table. 0.1, 0.2, 0.4, and 0.8. And because my B term, that is the number in parentheses, is bigger than 1, this should be an exponential growth function, right? I should end up with a graph that's going up. And if you look at our graph, notice they've plotted the points here, right? Here is When x was -2, y was 0.0125. It's kind of hard to see there. Let's jump all the way over to x equals 0. When x equals 0, y was 0.05. When x equaled 1, y was 0.1, 0.1. When x was 2, y was 0.2. When x was 3, y was 0.4. And when x was 4, y was 0.8. There's my graph. We just graphed that exponential function. So one last thing we're going to look at. I'd like you to turn your notebooks to page 493. And you can see they're asking us to look at the function y equals 3 to the power of x. Well, this is really y is equal to 1. So a is 1 times my b, which is 3, which is bigger than 1. So this should be a growth function to the power of x. They want you to list some key features here, but what I really want you to do is look at part B. I want you to decide which one of these graphs would be the graph of that function. Now, there are two that we should automatically be able to rule out. We already said this is an exponential function, right? It's not linear. No, it's not d. I also said it was going to be a growth function, right? Because I just told you b is bigger than 1, 3 is bigger than 1. So it's not exponential decay. It can't be c. See if you can decide which one of these functions it would be. Now, one way to do that is just plug in some numbers, right? What's 3 to the 0 power? Well, anything to the 0 power is 1. What's 3 to the second? 9. What's 3 to the third? 27. What's 3 to the fourth? 81. Which one of my graphs shows me this? Well, when x is 0, y is 1. Well, maybe that works, right? But when x is 2, y is supposed to be 9. That'd be way up here. When x is 3, y is supposed to be 27. That'd be way up here. Doesn't look like it's going to be a. Does b work? Well, when x is 0, y is, it's hard to tell if that's 1, because look at my scale. I'm going by 50s. 2 is 9. 3 is 27. That could be 27. It's about halfway in between 0 and 50. 4 and 81. Yeah, 81 would probably fall about right there. So B should be our answer, right? The graph of y equals 3 to the x power would match up with B. So you will find your assignment on Canvas or in your textbook. You're looking for assignment 9.1. Your notes are going to be very helpful in this. So keep your notebook, don't put it away, have that out while you're working on this assignment, and good luck.